In this video, we will see notion of convex functions. These are certain nice functions which has certain properties, and due to these properties, it is very easy, or it is relatively easy to obtain an optima or minima for this kind of functions. We are interested in this kind of functions because the loss function that we have defined for a linear least square regression is also a convex function. We'll see it later. But in this video, let's analyze few properties of the convex functions. So let us start this video. So a convex function is defined. So let's consider a very simple function, that is single variable function for now. So if f is the domain is R and codomain is also R. So it is single variable function. It is convex function if and only if any one of these three conditions are satisfied. So when we say any one of these three conditions satisfied, that says that all these three conditions are equivalent. So 1 implies 2 bidirectionally. Similarly, 3 implies 2. And a convex function satisfies either 1, 2, 3, or even if you prove any one of the condition, you can say that the given function is convex. So let's dwell into this condition specifically. The f is convex if for any 2 points, x1 and x2, belongs to R, and there is certain alpha in 0 and 1. F evaluated on this alpha times x1 plus 1 minus alpha times x2 less or equal to the alpha times f of x1 plus 1 minus alpha times f of x2. Now, when it comes to convex function, it is it's very good if we can if we do visualize it using certain diagram. So can somebody tell me from the group what is give me some convex function of f in a single variable f of x. Okay, I will take it x square. Thanks, Rohan. I was going to take that only. Why it is x square? We will see it through certain properties of the curve of x square that we will be seeing. So this is x axis. This is y axis. Fine. Now the curve of x square, how it will look like? If you plot it, if you remember the discussion of the curve sketching, you should be aware of it that we have done in the calculus lectures. It will look a bowl kind of shape. So these are the functions which are upward parabola bowl kind of shape, right? So these are functions which are generally convex function. So you take 2 points as per the first property of the convex function. Let's say this is x1. You take another point which is x2, let's say. You compute a midpoint between these two lines. I have drawn these two lines, or midpoint or any other point you can compute, doesn't matter. So let's say I'm considering this point for some alpha. Then the line evaluated joining the function value f of x1 and f of x2 has a more value than the functional value. So more specifically here x1 and x2. x1 and x2 is certain coordinates of x. So x1 is on x-axis. So I should write it like this. Similarly, x2 is on x-axis only. So I should write it like this. And the function evaluated on it should be written as a f of x1 and f of x2. That is a y coordinate. Everybody is fine with this, hopefully. This is a standard way of drawing the curve. Now, take certain point. What I am saying, do certain alpha. So alpha times f of x1, 1 minus alpha times f of x2. So you consider this line. If you take this point x, let's say this x at this value, and x is a certain linear combination of alpha times x1 plus 1 minus alpha times x2. Then whatever the line you are joining, the value of that line will be more than the functional value. More specifically, the orange point will be more than the yellow point. That is a functional value at that particular x. That's what I have written in the first definition. So f evaluated on that point, that means functional point, that means the yellow point, and the point joining one line, that is this line. This is a pink point. So everybody is clear this what this property says. You take any 2 point adjoining the line between those 2 points. The value on the line will be higher than the functional value. Everybody is fine with this. I will need your response. You have to understand this property. This is true for every x1, x2. This is not true for only one. This is true for any x1 and x2. Okay, fine. Hopefully got it. So another thing is saying that for any small epsilon r, f of x plus epsilon will be larger or equal to fx plus epsilon plus f prime of x. So f prime of x is nothing but through the, if we know the visual interpretation of the gradient, f prime of x indicates the slope of the tangent at that particular point. So I'm considering this x only. Now consider a tangent. Now you consider a small epsilon. You consider a small epsilon and evaluate it on a x plus epsilon. Evaluate the function on x plus epsilon again. Now the function value will be larger. That is, this pink point will be larger than the value on the line. That is the yellow point. So anywhere, everywhere, you draw a tangent somewhere else also. So let's say I'm drawing a tangent here at another point. Let's say I'm drawing a tangent here. Take a slight deviation from this. Evaluate the value on the tangent line and evaluate the value on the function. Function value will be always large everywhere. Another way of saying it is you draw a tangent, it will only pass through only one point. Tangent will not pass to any other point in this particular curve. So this second property is clear to everybody. I will need your response. Otherwise, I will not get what you have understood.
Sir, can you explain this part once again? I didn't get this part.
At every point, you draw a tangent. So let's say I'm considering this x point only. Every point you draw a tangent, you take a small deviation, epsilon. Now you evaluate the value on this tangent that is being evaluated with, let's say, a yellow line. So this is the equation on RHS. This is a yellow part. This is the equation on RHS. Fx plus epsilon times f prime of x. So this is the equation on RHS, right? This particular value. This is a yellow value. And what is the equation on LHS? LHS is nothing but f evaluated on x plus epsilon. So f evaluated on x plus epsilon is this only. So this is a pink value. So this is a pink value. And the third property says that f double prime of x is always greater or equal to 0 for all x. Please note these properties are for all x. If it is satisfied for all, then only we can say that it is convex function. If it is satisfied for some x's, some x1, x2, then no. It should be satisfied for all. F double prime of x, that is a second derivative, will be greater or equal to 0 for all x. The way of interpreting it is I will draw a new diagram so that I can draw a tangent and it's visibly good. So f double prime of f double prime, that is the second derivative. What does it indicate? First derivative indicates the rate of change of function. Second derivative indicates the rate of change of gradient, right? So what does it say? The rate of change of gradient will be more. So the gradient value need not be positive, but the change in the gradient will be positive always. So that means here, if you see the slope of the tangent at this point is a certain negative quantity, but as you go further, as you go, as you move on the x-axis direction, the slope will be increasing. So earlier it was very high negative value. Now it is slightly low. Now it is slightly low. At some point it will become zero. At some point it will start increasing, and it will only increase. It will never decrease. That's what it says. This is the third property. This says that f double prime of x is greater or equal to 0. The next gradient that you are evaluating is always larger than the current gradient. I will take one comment. Yes, Rohan, if you want to say function is convex in certain domain or certain interval, then you have to make sure that it is satisfying the condition in that interval. Any doubt, anybody in any of these 3 points? Varshita, Anisa. Okay. Varshita, it's fine. Okay. So now let's come to the multivariable case. If f is not a single dimension function, but it is of a multiple dimension function, then let's say it is function of r to the d. So the analogous conditions are this. This is the first condition, which says that the line evaluated on certain point in between will have a larger value than the functional value. Similarly, draw a tangent and evaluate function on the tangent point. The function value will be more than the tangent value. And similarly, this is called as a second derivative. Mostly you will not be aware of it. This is called as a second derivative or a Hessian of the function f. It is saying that greater or equal to zero, or more specifically, it is writing it is to be written as a positive semi-definite. Okay, don't worry about it. You should not be afraid of it. Whenever it is required, I will refer this property. Okay. Yes, in LA you have learned it. Hopefully, everybody has learned what is a positive semi-definite matrices. Everybody, right? So this is the last property, which is somewhat similar, which is saying that double derivative should be greater than zero. It is saying that the Hessian should be greater than. Hessian should be positive semi-definite. That is the condition. All of them are equivalent condition. Any one of them should be satisfied. So this is a vector form of it. Do not worry about it if you don't understand it fully now. But try to analogously see the conditions for the single variable function. The nice thing about convex function, why we are worried it is if you have certain, if you compute certain gradient and if it is zero at certain point x star, then this x star is a global minimum. You don't need to compute the second derivative and you can directly equate the gradient to zero and compute the global minimum. That's why the convex function are very nice here. Visually, if you want to see, whenever the gradient is zero, there is only one point, or there could be multiple point, but all of them will have a same minimum value. So whenever the tangent slope is zero for the single variable function, or whenever the gradient is zero, that point is a local minimum, or that point is a global minimum. Everybody is okay with this. In this function, it is clearly visible where it is zero. At the minimum point, it is zero, right? Here it is zero, everybody. Okay. So few things, sum of any two or more convex function is also a convex function. There are many ways of proving it. You don't need to worry about proof just for the understanding. I have written it. Consider two function f1 and f2. They are convex function. By the property, take a first property. This is just a first property, which is saying that the line evaluated on any midpoint will have a larger value than the function value on that point. This is true for both f1 and f2. If we do let f be a sum of this function, then do the LHS and RHS sum. So if you simplify this equation, you will get the final answer, which is the this is saying first property for a function f. That is a sum of these two functions. I don't you don't have to worry about the proof. You just understand it intuitively. So as Rohan has mentioned, let's say x square is convex, x to the power 4 is convex. You add them. The x square plus x to the power 4 is also convex. Okay, so everybody remembers what was the least square error function that we have defined. xi was a certain xi was a certain vector. W is certain thing that has to be computed by a certain level. So what is input, what is fixed, what is output? I will again ask everybody. Tell me what is input. Xi. Very good. Bharat is also. Okay. What is output? That has to be computed. Y. Wonderful. And what is the parameters? Parameter is W. So this entire thing is a function of what? This entire equation is function of W because the other things are fixed. This is fixed. These two are fixed. Given input, it is fixed. Given training data, it is fixed. So this is a function of W. Okay. So the nice thing is this least square error function is a convex function. I will try to give a small proof. Okay. Don't worry about the proof. Understand it intuitively. This is a convex function. That's all I want you from. So let's consider a very simple case. In this least square error function, I am only considering this term. And here also I am considering xi as only one variable only. So earlier, if you remember, xi was of a d plus one dimension. W was also d plus one dimension. But here I am considering very simple case. Small x is also one dimension. W is of one dimension. And let's try to see whether it is convex or not. x and w both belongs to R. So if I try to differentiate this function, what I will get? 2 times x w minus y multiplied by x. If I try to differentiate it again, what I will get? 2x square. This is double differentiation. And you can see that it is always greater or equal to 0. Since it is always greater or equal to 0 for all x, you can say that this particular function that we have defined is a convex function. But we know that our function which is of our interest is somewhat a vector function. Plus, it is sum of all this vector function. We have already know that if I prove only one vector function, which is only one part as a convex, only inside term as a convex, then the sum will also be convex. So I have tried to demonstrate it through the very simple case that if it is of a one dimension, then you can prove it is a convex function. So currently we have seen that loss function for a linear least square regression is a convex function if we consider x and w is of only one dimension. But we will generalize it, and we will see that even if x and w are of a d plus one dimension, that is, we consider a function which is of a multiple input variables, then also this least square loss function is also a convex function. So we will see that in the next video. Thank you very much for watching this video, and we will meet you in the next video.